So this is how we create a graph using adjacency matrix. Hello everyone, welcome to Intellipaat's YouTube channel. This is the part 5 of the Python data structure series where we are going to focus on the graph data structure. So let's take a look at the agenda for this session. First of all, we're going to start with a basic introduction to graph in Python, and then we're going to discuss various types of graphs available to us. After this, we are going to take a look at various implementations of graph using adjacency list and adjacency matrix, and finally we will learn about the BFS and DFS traversal methods and shortest path. I hope the agenda is clear to you. So without any further ado, let's begin. Before we begin, don't forget to subscribe and press the bell icon to get latest updates from Intellipaat. So what exactly is a graph data structure? Graph is a hierarchical, nonlinear data structure that consists of nodes and edges. The vertex or the nodes are connected with each other through edges and show a link between them. This representation of the data points is called a graph data structure. If you can see in the example over here, we have 4 nodes, 1, 2, 3 and 4, and all of them are connected with edges. This is basically showing the relationship or basically a link between them. So 1 is connected to 2, it is connected to 3 and 4 as well. But 2 is connected to 1 and 3 is connected to 2 and 1. But 4 is only connected to 1. So these are the links or the edges between these nodes, which is represented in a graph data structure. Also, let's take a look at why using a graph data structure is advantageous over other data structures. Using a graph comes with a long list of applications that can be fulfilled with. Some of the famous applications of graph is a social media networking website. Obviously, most of you must be aware of Meta, which is formerly known as Facebook. Google Maps is also how you can make use of graphs and show a link between various data points connected to each other. The graphs are also multi-directional, unlike a tree data structure that we have learned about in the past session, which can only traverse in a finite path and only in one direction. Although we can also call trees as a special type of graph. But here with the graphs, unlike the trees, we can travel in multi-directional. So a node can be connected to either 2 or 3 nodes and it will be traversing back to it again. So that is the difference between a tree and a graph. The easier implementation of the graphs not only gives a better alternative to trees or other linear data structures like list or a binary tree, it also helps in performing operations like searching with an enhanced efficiency. And now that we have a basic idea of what graphs are and how we use it, let's take a look at a few categories of graphs that we have. So the graphs can be categorized mainly in 3 types. First is the directed graphs. So the directed graphs basically show a direction in the edges or the links between the nodes. Like you can see the direction of each of these edges we have shown in this particular diagram. Basically what's happening is edges are showing the links between the vertices, and they're directed either in the forward direction or in the back direction, and the directed graph contains the ordered pairs of edges. So this is all about the directed graphs. Then we have the undirected graphs, in which there is no direction whatsoever regarding the edges, and the pair of edges will be unordered, and because we don't know which direction it is going to go for. And after this we have the third category, which is the weighted graphs. So in the weighted graphs we have an additional value or weight associated with each edge to further create a more detailed graph. So for every edge there is a value or a weight. Now we know how much. Let's say for example these are kilometers for instance, and these 4 nodes are places. So these weighted value will basically show us kilometers to traverse back to each of these nodes. So this is kind of a detailed graph where we will have a relationship between each of the nodes showing the distance. And these type of graphs are often used while finding the shortest path for the graph. Now that we have a basic idea of how we use the graphs and why we use it and what exactly are those, we have also discussed the type of graphs, the weighted ones, the undirected and the directed graphs. So these are basically the major categories in which the graphs can be categorized. Otherwise there are plenty of other types of graphs we have. There is spanning tree also that you can learn about. So we're going to stick to these 3 for now in this session, and let's take a look at how we implement the graph using adjacency list and matrix. So an adjacency list is a way of representing graphs where each node or vertex is present on each index value and form a link with the adjacent vertices. This is an easier way to implement graphs, but it often shows less efficiency in searching operations. Now if you take a look at this example, in the image we have 1, 2, 3 and 4, which are basically the vertex or the nodes inside our graph, and each of these vertex or the nodes are forming a linked list with the adjacent nodes. So for the first node, we have 1, 2 and 3 because those are the adjacent nodes to that particular vertex. And after that we have 2, which is only sharing the adjacency with 0 and 2. Then we have 3, which is sharing the adjacency with 0 and 1, and for the fourth it is only 0. So this is all about the adjacency list. We're going to learn more about how we can implement adjacency list to represent graph using Python in just a while. Before that, we'll discuss adjacency matrix. So the adjacency matrix is also how we can represent a graph data structure. And there the vertices show the edges in corresponding values in the matrix. There we have a matrix for each corresponding value. If it is an adjacent node, it is going to be shown as 1 in the matrix, and otherwise it is going to show 0 in the adjacency matrix. So this is a much more efficient way of representing graphs for better searching operations. It gives us better time complexity than the adjacency list. Before moving on hands-on part, I want to discuss the DFS and BFS algorithms also, which is nothing but a traversal method to find the shortest path in a graph. So let's discuss depth first search in the beginning. So the DFS or depth first search is how we can traverse the graph and also find the shortest path to visit each node. So here we have to follow a few steps, or you can say these are the steps you have to follow to do the depth first search. So first of all, what we have to do is we have to categorize two areas, which is visited and not visited. And after this, we put one of the vertices on top of the stack. So here we are going to use a stack, and there is a list of all the values that has been visited.
Just a quick info, guys. If you want to make a career in software engineering, then Intellipaat provides an advanced certification program on software engineering and application development by ENICT Council of IIT Guwahati. And it is taught by IIT Guwahati professors and industry experts. This course is designed to upskill and land your dream job. Now let's continue with the session.
So we put one of the vertices on the top of the stack and then put it out of the stack, and whatever values that are corresponding to it, the adjacent values, we are going to put inside the stack, and one by one we are going to check if that particular value has any adjacent nodes or not. So for 1 we have 2, 3 and 4. So we will push 2 in the visited list. After, when we check for 3, we have 2 and 1 which are already there in the visited list. So we'll push 3 into the visited list again. And last but not the least, we'll be left with 4, which has 1 as the adjacent node. So we'll push 4 in the visited list again. So the traversal for the DFS will be 1, 2, 3 and 4. So that's how you calculate the depth first search for the shortest path of any graph. Since we have only a few nodes over here, this may seem a little bit easier. But if we have, let's say, 15, 20 or 30 nodes, then it becomes a little bit trickier. And that's why we have to follow these particular steps in order to get the efficient values for the DFS. Moving further, we have the BFS or breadth first search traversal. So the BFS is also a traversal method where we can calculate the shortest path to visit all the nodes in the graph. Now here the only difference is, instead of a stack we have a queue. So we do the same things. We put one of the vertices at the back of the queue, and we check for all the adjacent values. If it is not there inside the visited list, we will put that particular node inside the visited, and after that we'll check for 2, we will check for 3 and for 4 again. So the next step will be, we pop the item in the front of the queue and push it into the visited list. For each adjacent node that is not in the visited list, we push in the back of the queue and repeat until all the nodes have been visited. For the BFS, the values will be 1, 2, 3 and 4. So you'll be able to understand this better when we are working on a live example. With that, let's move on to the hands-on part, and I'll show you how we can implement the graph data structure and all these BFS and DFS algorithms. So first of all, to implement the graph data structure, what we are going to do is we are going to use an adjacency matrix. So like I've told you, in the adjacency matrix, what we have to first create the adjacency matrix. For each index or for each value of the vertex, we have to find the adjacent matrix and add that particular value in the adjacency matrix. To do that, we have a class over here which is graphs. This is basically taking the size of the graph over here, or the number of vertices that will be present inside our graph. After this, we have a graph which is an empty list over here, and then we have a vertex which is also an empty list. To add the vertex inside, to create a vertex in this, we have created a function over here which is going to take this value v. This is going to be the value for each of the vertex that we are going to take from the user, or whenever we are calling this function. So if v is already present in the vertex, we're going to pass. So let's say if I pass the same value again, it is not going to take that value. And then what we have to do is we have to append that particular value inside this list. So let's say if I add vertex 1, it has to be appended in this particular value. After this, what we have to do is we have to also add the zeros inside the graph again. So for that, we are using another for loop, which is in the range self.size. Size is nothing but the number of vertices that we have given. And for that, we are using this temporary variable, which is also an empty list, and we are appending zeros in that graph. So that is how we are going to add the vertices in our graph. And after that, we have to add the edges again. For this, we are taking the parameters v1, v2 and e. So this is going to be a weighted graph, guys. So e is going to be the weight, and v1 and v2 are going to be the vertices where we are going to show an edge or basically link them together. To do that, what we are doing is finding out the index at v1 and v2 from the vertex and adding that weight on that particular indexes at the graph that we have created over here. Now to remove those edges, what we have to do is just make this value 0, because if there is no weight over there, that's bound to be there is no edge over there. Here we are following the same approach, v1 and v2, wherever we want to remove an edge, and we're just basically getting the index values and making that particular value 0. Now to print our graph using the adjacency matrix, we are taking two loops, which is a nested for loop. First is going to iterate over the entire size, and the second one is going to print only the values that we want, which is the vertex at the index I, the vertex at the index j, and then we are going to put the graph into our picture, which is ij values from the loop over here. So this is how we create a graph using adjacency matrix. We'll come back to how we are adding values and everything. Before that, let's just discuss the adjacency list also. Now to do that, we are basically doing the same thing. Instead of graphs where we have used it as a list, we're basically using a dictionary now. So for each value of the key will be the vertex, and the associated adjacent edges will be the values associated with it. To do that, now to add the vertex, we're just adding the index over here in the dictionary, which is going to create a key for that in an empty list. Now this empty list is going to be the value where we add the edges. Now to add the edges, what we are doing is we are creating a temporary variable where v2 and e is the temporary variable. It's basically a list where we are adding the v2 and e, which is the second vertex and the weight associated with it. Then we are appending it to graph of v1. Then to delete the edges, we're basically doing the same thing. Whatever values are there on that particular key value, we're just popping it. Now to print this, we are again using the nested for loop, and this nested for loop is going to print the weights, the I and j value. Now let's go back to our adjacency matrix over here. We have created an object graphs which is having 4, the size is equal to 4. Now we add the vertex 1, 2, 3 and 4, and we add the edges also. Now before adding the edges, let's just see how our graph looks like. Okay, so we are printing the graph. We have not yet allocated any values to it, so we'll just print our graph using the function. So this is how it looks. We have 4 vertices, 1, 2, 3 and 4, and these are the edges that we can create, and we can add the weight to it. Alright, so now what we do is we add the edges to 1 and 2, 1 and 3, 2 and 3, 3, 4 and 4 and 1 with associated weights with all of them. Now when I print it, so this is my graph with all the weights, and this is how the adjacency matrix looks like. Now coming back to our adjacency list, we're doing the same thing. All the 3, 4 vertices are there, and we are adding the edges again. But you will see that the adjacency matrix was a little bit different. The adjacency list is a little bit different in a way that it is a dictionary, not a matrix. But the values are going to be same, because for the first vertex, the adjacent values are 2 and 3. The weight is 1, and for the vertex 2 we have 3, the adjacent vertex, and the weight is equal to 3. For third it is 4th, and the weight is equal to 4, and for 4th it is 1, and the weight is equal to 5. So that's how we have created or implemented the graphs using adjacency matrix and adjacency list. So guys, if you have any questions, you can mention them in the comment section below, and if you are having any trouble understanding this, we have classes and objects session on Intellipaat that you can refer to, and that will help you understand this better and go through the previous sessions from the data structures series, and you will find out that these are very easier implementations that we are finding out. For binary trees and for linked list, it was a little bit trickier than this, but this is a very simple implementation using just a few functions and the classes. So this is how we have created the an adjacency list, which is nothing but a simple representation of this graph. Now to come back to our session, let's discuss graph traversal using breadth first search and depth first search. So here we have taken a custom graph over here. So here, let's say we have, this is nothing but an adjacency list if you can look closer. And the only difference is this is a hashable list, all of these values. And instead of weights, we just have the adjacent vertices. So for 1 it is 2 and 3, for 2 it is 4 and 5, for third it is 6, for fourth it is nothing, for fifth it is 6, and for sixth one it is nothing. Alright, so to do this we have created the visited and a queue. So if you remember, while I was talking about the BFS, we have to create a queue and there has to be a list associated with it, which is visited. Now this is a simple function that we have created. This has 3 values: the visited, which have already created. There is a graph that is going to be this one, which you are going to pass, and the node. So node is going to be nothing but where we are going to start with our BFS. So it's usually going to be the first vertex where we are going to start with it. So that's what we have also done. Now to understand this function, we have first of all visited where we are appending the node, and we have a queue where we are appending the node also. So now while the queue is there, we have to pop each of the items from the queue, or the first item basically, and we have to print it. And for neighbors in the graph, so we have to do the same thing again for all the nodes that has not been visited. So that's why we have created a simple expression over here. If neighbor is not in visited, we are appending the same values like we have done in the beginning. Again, we have created a simple function to implement BFS. Now to run this, we are getting the values 1, 2, 3, 4, 5 and 6. So this is how easily we can create a simple graph traversal method using a BFS. After this, let's also discuss the depth first search. We are using the same values for the graph over here, which we have used in the BFS. Now here, instead of just a list, we can create it as like this also, just like what we have done over here. Now in the function over here, we have the same values: the visited, the graph and the node. Basically what we are doing is, if node is not present in the visited, we have to print the node first of all, and we are appending that particular node inside the visited list again. And then for neighbors in basically the graph of whatever we have created, if it's not in visited, we are following a recursive approach here, which will do the exact same thing for all the nodes. And that is how we have done the DFS also. So the values are 1, 2, 3. Okay, so 3 will come in the end. So we have 1, 2, 4, 5, 6 and 3. So this is how easily we can learn about these values, like BFS and DFS traversal methods. And now that we are done with this session, if you have any questions, you can put them in the comment section below, and stay tuned for the upcoming sessions in the data structure series. We're going to cover searching and sorting algorithms in the final part of this data structure series. So thank you and see you in the next session. Now that we are done with the session, don't forget to subscribe and press the bell icon to get the latest updates on Intellipaat.
Just a quick info, guys. If you want to make a career in software engineering, then Intellipaat provides an advanced certification program on software engineering and application development by ENICT Council of IIT Guwahati. And it is taught by IIT Guwahati professors and industry experts. This course is designed to upskill and land your dream job.